Okay, folks, so first of all, really sorry about Thursday. I've got a very nasty bout of acute food poisoning the night before, and I did my best, but I came to the decision at 5 o'clock in the morning that it wasn't going to be very sensible for me to try to deliver that session. So I am really sorry about that, and this is a way in which I can talk you through precisely what we were going to do in the session, but that you can do it from the comfort of your own home. So what I'm going to do is take you through pretty much what we'd have walked through in the workshop, and I'm going to do this via point and click that you'll see on the screen in a moment. And this would probably be good if you I imagine this is probably going to be a pretty good way for you guys to follow it, because you can pause this video when you need to, start it when you need to, go to the place where you need to find specific pieces of information. So hopefully this will actually be quite a useful resource for you. So what we're going to do then, first of all, is we're going to go into Moodle. So if you open up Windows Explorer here, and essentially find the Moodle page, and then on that page you'll have advanced quantitative and qualitative research methods, and this is what you'll see. This is kind of the home page for the unit. Now we're going to do the workshop materials today, so I'm going to click on workshop materials there, and in that folder you'll see a number of things. You'll have the data set that we're going to work through today, the syntax that we're going to work through, the checklist, the dataset key, and the data screenwriter. Is kind of how it's written up, and I've presented that in the lecture. So the first thing I'm going to do then is get you guys to click on the workshop data, and we're going to open it up. Now this is an SPSS data file, and essentially what this contains is some real data that I've collected quite a few years ago now, 6 or 7 years ago now, with youth sports participants, so kids playing football basically, and I've measured a number of things. In the dataset key, those things are listed here. So the instrument 1 is a task and ego orientation in sport questionnaire. So this is kind of achievement goals, which I'm sure you're all familiar with from the psychology lectures. So essentially they measure things like a task and an ego orientation, and we've got 7 items that measure task orientation, and we've got 6 items which reflect an ego orientation, and I've listed them here. Okay, so if we click on variable view in the SPSS data set, you'll see that we've got ego and task items listed here. And the second instrument that I collected was a measure of engagement. And really I was interested to know how engaged young people were in sport. So did they feel that they were confident, dedicated, enthusiastic and vigorous towards their activities in sport? And it's just kind of a very soft measure of how engaged young people were in their sport. So this sample, we measure things like confidence, dedication, vigor and enthusiasm, and there's 4 items for each of those particular aspects of engagement. I've listed here in the label the precise wording of each of the items. Okay, so if we go back to the data view, just straight off the bat, you'll see a few things. First is that I've listed a unique participant ID, and that's going to become evident why that's important as we go through this workshop. I've got age here as a sort of continuous variable that runs all the way from, I think, about 11 to, there might be a couple of 16 or 17-year-olds in this sample. So early to mid adolescence. Gender, I've just coded 1 and 2 for male and female. And then I've got a soft measure of how many years these individuals have been playing sport for. The other thing you'll notice is that this data set is incomplete, and I've listed variables as missing. I've coded them as 999 as I always do, and as I recommended that you do in the lecture. So let's say, for instance, I'm just going to remove this item just to show you how this works. Let's say, for instance, you're entering this particular variable and you come across participant number 44 who happens to have a missing item for task orientation item 1. Now, when you come across this scenario where there's missing piece of information, as I've said, make sure you code that as a unique value. Now, in this case, we're going to code it 999, but if 999 is within the range of conceivable values, then code it as maybe 9999 or 99999 or whatever is an inconceivable, impossible value, so that we can eyeball the data very easily and look across to find those missing pieces of information. Can you see? So we've got quite a few pieces of information. We've coded them as 999, and we've told SPSS in the missing values column here that basically this is the default. My missing values are discrete. I've labeled them, and they're called 999. And when I've done this, for every variable in my data set, I'm telling SPSS that when you come across a value of 999, that is a missing value. Okay, it's not a real value; it's a missing value. So that's the other thing you'll notice in this data set is missing pieces of information, large number of individuals, and really the theory or the kind of the purpose for collecting this data is to see whether achievement goals are correlated with engagement. And so that's why we went out in the field a few years ago to try and collect some data on that particular research question. Now, of course, your research questions will all differ. Some will be physiology based, or contain items like VO2 max or some biological measure or height, weight, some personal characteristics, maybe maturation. So there'll be other things that you guys will have measured. Of course, this won't completely overlap with some of the types of items that you measure, but nevertheless, you will still enter the data in exactly the same way, and you will still code the data in exactly the same way. You'll just have different measured variables within your data sets. Either way, when you undertake research, you're always going to have messiness. There's always going to be pieces of information missing. And so we need to find a way of effectively estimating these values without ditching the cases altogether, because as we talked about in the lecture, we don't want to lose information. We want to obtain as much information as possible, but we want to retain the information. We want to retain the information in the most appropriate way. All right, so that's our data sets. And the first thing that we're going to do before we do anything else is to inspect the data for entry mistakes. So are there any values in our data set that are beyond the range of possible values? Or is there anything that particularly sticks out as a very, very, very unlikely response score? So the way that we're going to do that is very simple. We're just going to go to Analyze, and we're going to just list off some descriptive statistics. All right, very, very straightforward. You'll have done this before in research methods courses previously. So what I'm going to do is go to you can display variable names, might be easier. So right click, display variable names rather than labels. This probably makes this task a little bit easier. What I'm going to do is click on Ego1. I'm going to hold down Shift, and I'm going to go right to the end of the variables that I've collected data on. And then I'm going to move them all here into my variable list. And then all I'm going to do is click Options. And what I want is minimum and maximum. The minimum and maximum value for the data that I've asked for there. And now instead of clicking OK, I'm going to do something slightly different. I'm going to click Paste. And what Paste will do is it will bring up that command as syntax in SPSS. And all I'm going to do here for this process is list this syntax as here you can see all I've done is I've told SPSS to ignore this line of command by essentially putting 3 asterisks. That's to say, SPSS, please ignore this script. And then what I've done is listed or pasted in, I should say, the specific command I'm requesting SPSS to do. And here you can see it's the descriptive command. Give me descriptives for variables which equal the variables that I've asked for. And then the specific statistics that I want is the minimum and maximum. And that's all we need to do. So what I'm going to go ahead and do now is just highlight that script, click Run or Play here, and SPSS will run that particular analysis for me. Now here you can see that we have a couple of values that are outside the possible range for the scales. All of these scales run from 1 to 5, so anything above 1 or below 1 or above 5 is an impossible value. You can see here for this item I work really hard, we've got a value of 33. And for this item here, I am devoted, we've got a value of 55. So clearly both values are beyond the range of scores. So what we need to go and do then is identify those values and rectify the problem. So if we go to variable view, I work really hard is task item 4. So we double click on 12, which will take us to task item 4 here. And then I'm going to right click on that, and I'm going to sort the values by descending. Okay, so that'll give me the largest value first and the smallest values last. Here we go. We can identify this particular problematic individual, and we can do one of two things. So this person has been given 33. Now we can make an educated guess that that's probably meant to be a 3. But there are a couple of better ways we can go about rectifying this problem. The first is that we can go back now and identify the unique participant ID of this particular case. So you can see here, it's ID number 205. All right, 205 is this case where we've got this erroneous score. So if we've listed on our questionnaire that, or we've written down on the questionnaire that this case is 205, then we can go and find 205 in our stack. We can go back to the data and look to see what they would have reported or what they have reported. So let's say in this case that they've reported it did indeed report 3. Gone back to data, we've checked it out, and replaced it with a 3. And I'm going to do exactly the same for I am devoted. So here, go to the I am devoted item, which happens to be dedication item 3. Exactly the same. And we find here that this is now participant number 38 who has this problematic score. Now, as you can see, every time I'm sorting these cases, I'm scrambling the data, right? So if I don't put a unique participant ID, then I couldn't go back and find the questionnaire because I haven't organized my data properly. So this is why the participant ID is so important, because as we continue scrambling the data, the participant ID holds those values constant. It lets us know exactly which individual we're interested in. So here you can see this was a score of 55. We've gone back to the questionnaire, and indeed they did score a 5, so we'll replace this with a 5. After that, everything else looks in order. So as a very first step, we've identified some scores that are impossible values, and we've rectified the situation. So that's the very first step. So I'm just going to remind myself in my syntax that I've replaced the data errors. Okay. Right here, data errors rectified. All right. Awesome. So we've identified any data entry mistakes, and we've rectified them. The next thing now we need to do and to move on to is the missing value analysis. Remember, I talked about how we need to identify how much data is missing and then why it's missing. So is there a systematic reason? So missing value analysis within SPSS is the way that we do that. So once we've identified those data mistakes, we've rectified them, the next step is to go to analyze missing value analysis. And again, display variable names here, move all of our variables over to the quantitative variable. And we need to do a couple of things. We need to click on expectation maximization. Okay, that's the algorithm that we're going to use in the first instance to identify patterns of missing data. And we're also going to click on patterns and click display cases, tabulated cases, grouped by missing value patterns, and then cases with missing values sorted by missing value patterns. So that's going to give us those patterns of missing data we talked about, so we can identify any trends. Just make sure, yeah, that's fine. And then again, we're going to click on paste, and that's going to paste it into our syntax. I'm going to tell myself what this means, and essentially this is missing value analysis. This is what this syntax means. And then I'm going to highlight it, and I'm going to run it. Okay. Now I have a lot of data tables that kind of might look a little bit scary at first, but if we break them down, it becomes much easier to understand what's going on. So you can see here that these are just the basic statistics for each of the items that we've collected data on. N is the number of complete cases, so that's to say the number of cases for which you've got complete information, no missing data, and then the means and the standard deviations, and then the number of missing of these particular items. So for ego item 1, we've got 3 pieces of information missing, which is equates to around 1.2% of the sample. Okay, and this is kind of like a distributional one. How many extremes do we have on each of these particular items? Which is kind of an interesting one for distributional stuff. The summary of estimated means, essentially, remember I talked about expectation maximization, preserving the underlying characteristics of the data set. Well, this is essentially what's happening here. We've got a mean for all values observed data and an estimated maximization mean. So that's to say that what would happen if we could estimate the values and how closely would those means match with the actual means. And you can see here they match very, 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 very closely. But we don't need to worry too much about that yet, because one of the first and most important things that we need to identify is, okay, how much data is missing, and do we have any individuals in this particular data set that have too much data missing? So I talked about a criteria for too much data missing being be it over 10%. So anyone with 10% or more has got a lot of missing data. All right. So you can see here that across this particular sample, we've got a couple of individuals here that have got a lot of missing data. So case number 73, and that's SPSS case 73, not unique identified 73, has a lot of missing data, 17%, and 222 seems to also have quite a lot of missing data. So there's 2 potential people here with too much missing data, but everyone else seems to have quite a low amount, relatively low percentage. So that's quite good. That means we can handle that quite easily. These are just the patterns of missing data, and there's very few patterns. So that's good news for us, because that suggests that there's no kind of uniqueness to the data being missing. It seems to be quite random. And here is the Little's MCAR test that I talked about, that test of whether the data is completely missing at random. And remember I said we wanted a non-significant chi-square. That's to say that there's no significant difference between the means and variances of the complete data set versus the data set with incomplete information. You can see here the significance level is above 0.05. Therefore, we can conclude that in this data set, the data is missing completely at random. And that's really good news, because what that means is we have a little bit more flexibility in terms of how we imputate those values. So Little's MCAR test suggests the data is missing completely at random, which therefore means that we don't necessarily have to preserve so much information. So if we've got individuals in our data set that have large amounts of missing data, then we can just remove them from the data set, because there's no systematic nature to the missingness. They're just a random individual with data points that are missing completely at random. So 222 here's got 10.3%, so we can go to 222. Here, 222, I'm just going to right click and I'm going to clear. I'm going to get rid of them from the data set. They've got too much missing data, and we're okay to do that because data is missing completely at random. Again, number 73 is missing. Too much information, so we click on number 73 and we clear that case. Always delete biggest first and smallest last. Why? Because when we delete these cases, it pushes the data up, so that if we're then deleting someone further down the data set, what that means is that essentially that this number no longer correlates with where they sit. And so if we've deleted 73 first, this would now be 221, not 222. So always delete the first, always delete the highest case first, moving down to the lowest, so you don't run into that problem. So in this case, that's how you would go about removing those outliers. And because I've scrambled the data set, guys, this might be different in your own examples. When you go through this data, these might be slightly different numbers. Okay, but don't worry about that. These numbers will stay the same. So always delete the highest and then the lowest. These are just kind of the correlations. So remember I said we kind of preserve the underlying properties of the data set. That's to say the correlations, the means, and the variances. So this is kind of all the expectation maximization is doing. Okay, so we know the data is missing completely at random, and we've removed individuals that have too much information missing, as I say, more than 10%. So let's now move to how we're going to imputate these values. Actually, just before I do that, I'm going to go back to the syntax and just give myself a recap of that process. So we know that the note there's no differences. Between n car is assumed. Two participants removed. With more than 10% missing data. Okay. All right. Good stuff. So we've done that. Now we're going to move to how we imputate. Now remember I said that if the data is missing completely random, we're more flexible. And the best and most straightforward way to imputate the data would be regression, particularly in this case where we've got a lot of related points. So that's to say, if we know that certain items are highly correlated with each other, then we can safely assume that they are good candidate related points to make estimations of what would have scored had we had the data. So regression imputation is the way that we're going to imputate in this particular example. Because in your own examples, if you've got more difficult, let's say, missing data that's missing at random, or that you haven't got very many participants, it might be therefore that expectation maximization or multiple imputation is more appropriate. But in this case, data is missing completely at random. Got a lot of data. We can lose those that have got quite a bit of information missing, and we can imputate with regression imputation. And I would say, guys, this is the simplest way to imputate, and it's also the way that you're going to be imputating your data for your assessment. So this workshop will cover what you need to know to be able to do that, and there is nothing more complicated that you're going to need to do for the assessment in this module. However, it might be that in your own research projects you come across more complex missing data scenarios, in which case you would need to use other methods, and I've gone over those in the lecture. Okay, so if we're going to use within scale imputation, regression imputation, then we need to make sure that the scales are indeed highly correlated. That's to say that they're valid and reliable. So what I'm going to do first and foremost then is check that, just to make sure that the scales in this particular study are reliable. And you will have done this previously. This is not something that you should not be aware of, and in research methods that you've done before. If we go to analyze and scale and reliability, very, very straightforward. You can display the variable names, and all I'm going to do is take the task items here, move them here, and I'm going to call that task. All right, I'm going to paste that in there. I'm going to do the same for ego, scale, reliability, remove these. I'm going to do exactly the same for an ego orientation here. Ego 5, ego 6. Okay. I'm going to paste that in, and then I'm going to do exactly the same. Oops, sorry. For our engagement items, so I'm going to move these in. Take confidence, confidence 1, confidence 2, confidence 3, confidence 4. Oops. say confidence here, paste again. Remove those out. Dedication, 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 dedication. Paste that in. Bigger, 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 bigger. And finally, the final one here is enthusiasm. So again, I'm just going to label and remind myself what I'm doing here. I'm just testing scale reliability. And again, I'm going to highlight those and I'm going to run them. And essentially, scales are determined to be valid if they're above 0.7 for the Cronbach alpha. You can see here Cronbach alpha for task is 0.81, 0.83 for ego, 0.80 for confidence, 0.80 for dedication, 0.81 for vigor, and 0.76 for enthusiasm. So in this particular sample, all of those scales are reliable. That's to say that each of the items within scales is highly correlated with each of the other items. So this is really good. This shows us that we can now use this information to try to make estimations of what missing values would have been given scores on the other items in their scales. Okay. So I'm just going to again remind myself what this means. Scale reliability is good. Of 0.70. So I'm going to imputate remaining data with within case subscale mean. All right. Awesome. All right. So this is kind of regression-based imputation. All right. Now I'm going to do this with syntax. We can't do this in SPSS. SPSS doesn't have a point-and-click option for this. I have to do this with syntax. So what I'm going to do is go back to the Moodle page. All right. And I'm going to click on the workshop data syntax. Now you'll get a syntax file that looks something like this when you click on it. You go to the scale reliability part and you copy and paste all of the syntax that I've written out for you, because if I was to write this out, we'd be here all day, and I'm sure you've got better things to do than sitting in front of a computer watching me write script. So I'm going to paste that in here. So I'm just going to copy from the syntax file that's on the workshop and I'm going to paste it. Now these commands are going to basically replace all of the missing information for each of the items in our data set here with the mean of the remaining items. So let me just walk you through this SPSS script. So I'm telling SPSS, essentially, I'm using the if command. So if you find in the data set that ego1 is missing, okay, then ego1 equals the product of ego2 plus 3 plus 4 plus 5 plus 6 divided by 5. That's to say the average of the rest of the items. Again, if ego2 is missing, ego2 equals 1, 3, 4, 5, okay, etc., etc. So basically what we're saying is here, if you come across this item and it's a missing value, then replace the missing value with the mean of the other items in that scale. So let's go ahead and copy that syntax, okay, and run it. Now what you'll instantly see is that now we have no, or very few, well actually sorry, I should say no 999s in this data set. None at all. Okay, but what you will notice is we still have some gaps. And the reason why we still have some gaps is because this particular individual had 2 items missing, but they're missing on the same scale, right? Task 3 item and task 5 items missing. Okay, so if we go to task 3, the way that we rectify this is we find task 3 item, task 3 equals, and then instead of using task 5, we take task 5 out of that equation, and we simply take the mean of the remaining items. Okay. On task 3 here, run that specific line, and you'll see the value's been replaced, and then I can run the specific line for task 5, and the value's been replaced. Okay, I'm going to undo that because I don't want that to stay in my syntax. Now I'm going to look across the data set to see if there's any more pieces of information missing, any more gaps that we can identify in the data set, and we have one here. So task 1 is missing here, and task 6 is missing there. So again, we do exactly the same thing. We find task 1, we take task 6 out, and we change the formula, highlight that specific code, run it, which has then imputated the value here, and then we undo, take that off because we don't want to keep those changes, and then highlight the 6, run again. So again, I'll just come across the 6 here, 6 is here, and again, we've imputated that value. Now, I don't think we have any other errors in this data set. We don't have any more gaps. I know we do. We have one more here. So task 1 is missing here, and task 5 is missing for this individual. So again, we go back to task 1. We take 5 out, and we divide that by 5, and run. Imputates the value. And again, for task 5, we just highlight and run. All right, imputate the value. Okay, so I believe that's all. Yep, that's all. We can do a quick check to make sure that we've cleaned that appropriately. So go to missing value analysis and then just click OK. Don't need to paste this in. And you can see here no missing values. All right, no missing values at all present in the data set. So that's great. We've replaced the missing values with the scale mean, and we've done that through syntax. So we can basically now just write a new line in our syntax to say missing values successfully replaced with scale mean. Regression imputation. All right, so good stuff. So we've done that. Now the next thing to do is compute our variables. So we're going to basically now calculate our variables. Remember I said in the lecture that this is very simple, just aggregation of the items within the scales. So again, we can do this. We can do this in syntax if you want, or we can do it through computing variable here. It's up to you. It doesn't matter how you do it. I'm going to compute task variable first, and basically I'm going to say that task is a linear function. That's to say that it's an average of task 1 plus task 2 plus task 3 plus task 4 plus task 5. Okay. Divided by, wait, no, there's more than 7 items. 6 and 7. All right, divided by 7. Okay, I'm going to paste that in, and that is the syntax to compute task. Now I can do this by hand, the rest of them. So if you use the compute command within SPSS, and I'm going to compute ego, which equals ego 1 plus ego 2 plus ego 3 plus ego 4 plus ego 5 plus 6, okay, divided by 6, full stop, end command, okay, and then enter, so new line, and I'm just going to basically tell SPSS to execute that line as soon as computed. Then we can create a task and ego scale that way. Okay, so you can do it either way. You can do it through transform compute and you can pull them over, or you can do it by writing out the syntax by hand. I would get into the habit of writing out the syntax by hand. Programming skills are really, really important. And this is, and it's starting simple in terms of programming skills, telling SPSS what to do and then it run the function. You can go back to your syntax here that I've put on online, and we can highlight the rest of those commands there, copy them, and paste them in. Okay, so essentially we're not just calculating task and ego, but we're also calculating confidence, dedication, vigor, and enthusiasm, which is 1 plus 2 plus 3 plus 4 divided by 4. Okay, each of the particular items within each of those scales. So once I've done that and I've written that script, or I've done it in SPSS through compute variable, then I just highlight and run. And what that's going to do is put a couple of new lines in a data set at the end. Task, ego, confidence, dedication, vigor, enthusiasm. Okay, those are the key variables in this particular piece of work. So once I've calculated the variables, I now need to look at distributional assumptions and check the data for outliers. Remember, so we need to check for univariate outliers, so outliers on one variable, and multivariate outliers, outliers on 2 or more variables. So I'm going to first of all test for univariate outliers. All right, so what I'm going to do here is go to Analyze to test this. Analyze descriptive statistics and descriptives. I'm going to highlight all those variables that should be in there and remove them because I don't need them in there. And I'm just going to highlight the newly created variables, those newly calculated variables that we've just calculated. And I'm going to save standardized values as variables. And then I'm going to click on OK. And once you've done that, again, we'll have some more new columns, but these are Z-scores, okay? Scores that are transferred into units of standard deviation. And we can sort these scores to try and identify univariate outliers. And remember I said a univariate outlier is an outlier that is above 3.29. Okay, so if we have a score that's above 3.29, then we're so unlikely to have sampled it from the population, it has to be an outlier. And that's an outlier at the 0.001 level, so we wouldn't expect to sample it one time in 1,000. So if we click on task to start off with, we click on sort ascending, and you can see here that we have a couple of individuals that have Z-scores on tasks which are way lower than the sample. That's to say, we wouldn't expect to sample them one time in 1,000. So we are very clear on the rules for this, guys. If you identify people that are univariate outliers, they have to be removed from the data set. So I'm going to click on those first two participants. I'm going to right click and I'm going to clear. They have Z-scores that are too high, or in this case too low. I'm going to click on it again, right click on it again, they're going to sort descending, and we're okay. There's no one that scores too high, there's just a couple of people that score too low. The ego are going to do the same, going to sort ascending, they seem to be okay, going to sort descending, just about okay. Confidence, they're okay, they're okay. Dedication, they're fine, they're fine. Vigor, they're okay, they're okay. And likewise enthusiasm. 3.29, so we have to get rid of this person here for enthusiasm. So we click on them, clear them. And sort descending. Okay, so that's how we deal with univariate outliers. Okay, really, really straightforward. Doesn't take a great deal of effort to do, and if we identify them, then they are removed from the data set. Okay. So I'm just going to put here. Oh, I didn't paste that. So I didn't paste this in. So I'm just going to quickly paste that in here. So again, test for univariate outliers. Make sure you paste the save is basically the command for Z-scores. All right. So we've identified and removed 3 univariate outliers. All right. Okay. So once we've done that, we can get rid of these z-scores. We don't need them in the data set. So we can just highlight them all, clear them from our data set. Now we need to look at multivariate outliers. Slightly trickier, but nevertheless still relatively straightforward. So now I'm going to test for multivariate outliers. I say outliers on more than one scale. Okay. So here is, as I said, slightly more tricky, but nevertheless not too difficult. So if we go to analyze, we go to regression this time. We're going to test the linear regression. Now what I'm going to do is put task in the dependent variable and all the other variables in the independent variable. It doesn't matter what order you do them in, as long as all the variables are in a regression model. And then I'm going to go to options, and that's okay. And then I'm going to go to save, and I want you to save those Malabonus distances. Okay, so go to save, click on Malabonus distances, continue, and again we're going to paste that in. All right, so this is just a regression of all the variables in our data set, and we're saving Malabonus distances. We're going to click run, and again what that will do is it will give us a additional line in the data set of the distances that each of these individuals is away from the regression line for multivariate outliers. So I'm going to right click, I'm going to sort descending, and I'm going to go from highest to lowest. Now in this model, okay, we have a couple of important figures, but the most important is the degrees of freedom with this model, which is 5. We need to then look at a chi-square distribution to get a cutoff for that distribution at 0.001 level. So here we just need to find a chi-square distribution table. If you go in here, you can find them online very, very easily. Chi-square distribution table. We need to find one that goes to 0.001. So the first one that comes up here, 0.001 with 5 degrees of freedom. See here we're looking for a critical value of 20.52. All right, so you can find these tables freely available online. So anybody with a Malabonus distance above 20.92 is a multivariate outlier. You can see in this particular sample we have one of those individuals. So again, we need to clear them from the data set, and we are done. Okay. Again, in the syntax, always a good idea to remind yourself what you've done. So with 5 degrees of freedom, okay, one Malabonus distance above 20.52, which remember is a critical value, was identified and removed. If maybe you might say that this is P below 0.001. Let's say that it's smaller than 0.001. Alright guys, so once we've done that, we might just quickly check our normality. So we might just do a safeguard check and go, okay, let's just run some descriptive statistics here with skewness and kurtosis. Okay, click continue paste. So really what I'm doing here is getting distributional, checking distributional values of the variables. So if we run that, we'll find in our output that we have skewness and kurtosis values, and essentially the quickest and easiest way to check that these things are within reasonable rounds of significance is quickly get our calculator up and go, okay, standard error for skewness is 1.53. So if we go 3.29, which remember is our critical value for statistical significance times 0.153 for skewness, we get a value here of 0.50. So what that means is that essentially, if any individual or any variable in our data set is above that, significantly above that, then we can assume the data is normally distributed. You can see here that most variables fall easily below that, with the exception of enthusiasm, which has a slight negative skew, but that's nothing to be too worried about, because regression-based analysis can handle small deviations, which this is in normality, and we can do the same for skewness. So 3.29 times 0.304 equals 1. You can see here that all of the values here fall well below 1. Okay, in which case there's nothing to be worried about now in terms of distribution assumptions in these variables. They're pretty good, and as a consequence, we are ready to run analyses. All right, guys. So it'd be useful for you to save your syntax always. So save it somewhere, save this file somewhere that you can go back to and retrieve it. I would also advise you to print it out and put it in your portfolio folder that I will give you next week. I'm also going to put up a video that I recorded about how to do multiple imputation, because I think that would be useful for you to learn how to do that. So I'm going to also put a second video up that just goes over multiple imputation, because there'll be cases, particularly with physiology data and biomechanics data and so forth, where that particular imputation technique might be needed. So we'll put that online for you as well. As always, if you've got any questions, do please email me or come to see me in my office hours, and we can have a discussion about particularly around data entry and cleaning. But apart from that, apologies again for not being able to do the workshop, but I will see you next week when we're going to talk about correlation and regression.